many of the tests, a couple of them, and thought, they looked pretty solid. So, oh boy, oh, it moved my Zoom icon when I updated it. Okay. So let me just make sure a couple things are working here. And then we're going to start talking about, oh, just a second. We're going to start, can I zoom in and out? Okay, good. Oh, I should maybe pull that shade over there. You can see the reflection of the window. I've pulled the shades on the other 4 windows, 3 windows, but not that one. Maybe I will do that here in a second. Okay. All right, and there you get a lot of reflection because these whiteboard walls are very shiny. So there's the there's the ceiling lights reflecting in the wall. Okay, couple things organizationally for this next couple days of this week and beginning of next week. Let me see. We have class today. We're going to start talking about chapter 8. Obviously, that's kind of going back in the sequence. We did chapter 7 is about force, and that was a test, and then 9, 10, and 11 was the test on Monday. Chapter 8 is called motion in a plane, and a couple other things get talked about in there, in particular, some gravity topics. And where's the other chapter that talks about gravity? I'm just trying to find it here. Where is it? Chapter 13, Newton's theory of gravity. Really, it's those two topics together. Circular motion is the main topic from chapter 8 that is going to be pretty relevant. There's lots of circles drawn as I glance at the chapter summary page for chapter 8. And I think you can imagine circular motion is pretty relevant when talking about like planetary motion, motion of satellites around the Earth due to Earth's gravity, maybe motion of the moon around the Earth due to Earth's gravity, Earth around the sun, planets around the sun due to the sun's gravity. So we're going to be talking a fair amount about Newtonian gravity. And along the way, there'll be quite a few circular motion insights that we're going to make use of. So that's kind of where we're going next. I'm going to just bring up the course schedule. And where would that be? Right here. So chapters 8 and 13 is kind of the topic from today through about a week from today. And then chapter 14, what is 14? Some oscillation and rotation is what we're going to be doing kind of for most of the rest of the semester. From about this time next week on. Chapter 14 is oscillatory motion, and chapter 12 is rotational motion, and we're going to talk about things like torque and moment of inertia. So that's getting ahead of myself, but that's upcoming. This week, and I don't have this represented here, which this is the schedule that's right now on Moodle. This Friday is Good Friday. It's Easter weekend. Happy Holy Week. So this Friday, we would usually have Friday and Monday off at Northwestern around Easter, and I kind of wasn't thinking about that when I just shifted this around and wrote this up. So we won't have class on Friday. The homework that's listed for this week, I just put as due 6 p.m. on Monday. Just added that Moodle assignment. So you'll have time maybe Monday to ask some questions about these chapter 8 problems, just these 5 here from chapter 8. And then in talking about chapter 13 and gravity, there's some additional questions that I've written up on a handout, which I'll give you guys probably next Monday, and that'll be part of next week's homework due next Friday. So we're not going to have class Friday, which is Good Friday. What about Monday, Easter Monday? I'm planning on using a little bit of that part of that day to work on some new material with you guys. I think maybe it'll mainly be a video, maybe a short class period, to try to still have our Easter break and celebrate Easter. So no class Friday, and there'll be something that just keep an eye out, maybe on Moodle, or an email from me over the weekend about the specific plan for Monday. I think I'll probably put together a video, and you can watch that on stream, like, on your own time. And by next week, I'll have the test graded. I guess that would be the other thing to say. So just 5 questions this week. Those will be due Monday, all from Chapter 8. Next week is mainly gravity questions. Chapter 13 is gravity. The handout will be questions about gravity. And when I say gravity, if I don't clarify going forward for the next like week and a half, 2 weeks, if we say gravity, we mean not just gravity near the surface of the Earth, which is of course something we've talked about heavily since day 1 of this class. I would mean gravity between planets, moons, and stars. What I'm going to call what is often called Newtonian gravity, or Chapter 13's title is Newton's theory of gravity. So not just how does gravity work when you're standing on the moon or when you're standing on the Earth, but what happens, or how does gravity work over the large distances between astronomical bodies. So that's a couple thoughts about this week. And yeah, last week's lab, the lab is now, there's an assignment on Moodle just posted saying the lab is due tomorrow at noon. And I'm not super hard and fast on the due dates. If you tune in after that, that's fine. So basically the lab I kind of put as due tomorrow around the time of our lab times tomorrow morning, which is kind of late morning. What is due for that lab? That was the 2D collision lab. I'm just reminding myself. For the 2D collision lab, what you need to submit is just the file called a PDF of the worksheets, where you will have drawn, there's 2 worksheets, collision 1 and collision 2, and you'll have drawn a bunch of vectors on there. So that part would be something to submit. 2-page worksheet with a bunch of your vectors hand drawn with some measurements written in by you. And then the Excel file called data sheets, which you can just fill in some of the key values that you calculated into those couple tables. You'll see that if you look at the data sheets. And I think it's a couple key measurements to summarize momentum and kinetic energy for collision 1, steel, and then the same information to summarize collision 2, steel, plastic. Tomorrow's lab. Every week when I get to lab, both your lab on Thursdays, or close to your lab on Thursdays, or my other classes lab on Tuesdays, it is really kind of open-ended on how that's going to be conducted every week, because every lab activity is so different than every other one. We'll see how tomorrow's goes. We'll see how tomorrow's goes. It'll be about circular motion, which is the topic of Chapter 18. Okay, so I'm going to briefly talk about circular motion and do one or two calculations about circular motion, but mainly we're going to start to talk about gravity, Newtonian gravity, the gravitational field of the Earth extending not just to the surface, but up, into the upper atmosphere and higher up into orbits of satellites, and on out to, like, let's say, the moon. I should tell you up front, this is one of my favorite topics, so I can probably talk quite a while about gravity, orbits, planetary motion, the solar system, other things, galaxies, things like that. Let me show you a sheet that'll be up on Moodle pretty soon. And this will be a chance for us to start talking about circular motion, although the information you're going to see is about gravity, the gravitational field of the Earth. So what do we typically say for the gravitational field of the Earth? Little g, 9.8, maybe some books say 9.81 meters per second squared. So can you guys see that there? So this is pretty detailed measurements of little g at various locations on Earth, cities basically. And maybe just look this over a little bit. Variation, I'll zoom out a bit. Okay, I don't know, somewhere in between there. Okay. It's pretty similar at different points on Earth, but you can see it's a little bit bigger in some locations, a little bit smaller. There's an average 9.8008. That's just the average of all the numbers on this particular listing. I think it's about 57 or so different locations. And you might just look at this. They're arranged from lowest values on the left, getting bigger as you head down the column. So the biggest values are down here on the right. By the way, Minneapolis, Minnesota is one of the higher ones on this list, 9.824. You guys get a little bit more workout here in Minneapolis when you kind of go up a set of stairs than if you go up the same set of stairs, I don't know, in Havana, Cuba, or in Hong Kong, Mexico City, Kuala Lumpur, Kandy, which I don't remember where that is. So you can see it gets as low as let's say 775. So that's about 0.02 less than 9.8. And it gets about as high as, 9.825. So 0.02 or 0.025 higher than 9.8. So here's my question. Which locations, do you see any kind of any trends here? Do you see any link between the locations that tend, like geographically, what locations tend to have a little bit higher G values and what locations tend to have a little bit lower G values? Big locations are, Anchorage, Oslo, Sydney, Minneapolis, Copenhagen, Stockholm, Manchester, England, Amsterdam, London, Brussels, Frankfurt, Seattle. Smaller, lower locations, Mexico City, Kuala Lumpur, which is in Malaysia, Singapore, Jakarta, Bangkok. Any thoughts about what the key driving issue is there? Or what some of the driving issues, plural, may be? Altitude. So how do you think altitude would affect this?
The higher above sea level the place is, the lower the gravitational effect is.
Okay. So we could look this up. Singapore's right at sea level. Mexico City's got a pretty high elevation, and it has quite a high altitude, and it does have one of the lower values. I think Kuala Lumpur is pretty close to sea level. Sea level for Anchorage. Some of these are at decent elevations. What about in the middle of the list? Denver's got a pretty high elevation, right? Not as high as Mexico City, but it's kind of middle of the list, very close to 9.8. So I think there is most definitely an effect due to, trying to get back to Zoom. There most definitely is an effect due to elevation, but it's not the primary effect. So look at this. Where are these locations on the globe? Compared to what parts of the world are kind of near the bottom of this list? Well, I've lost it. We got a lot of Europe in here, right? We got a lot of Europe for the high G's and some North America for Minneapolis, I guess. Seattle, Vancouver. It has to do mainly with how close you are to the equator versus how far you are either north or south of the equator. So locations near I'm trying to write this in the chat, generally have lower G values. and vice versa. Locations far north or far south of the equator tend to have higher G values. Generally have higher G values. And I think you can kind of believe that. I mean, look at, Havana, Cuba, Rio de Janeiro, Kuwait City. It's not too close to the equator, but medium. Cape Town, South Africa. It's not too close. Los Angeles is, got a decent elevation, altitude, latitude. And we got a lot of Europe and North America here. I didn't share, sorry. Okay, so let's talk about why that is. Why is it? Why is it that points on the equator, if you measure G, if you drop things on the equator, they don't fall quite as fast? It's actually not because gravity is actually weaker on the equator. It's because the Earth is doing what? The Earth is a big ball, and there's gravity towards the middle. But what's the big Earth ball called the Earth doing? It's moving around the sun, and most importantly, it's spinning in place. It's spinning even if it weren't moving around. It'd still be spinning in place. And what happens to an object, like imagine you were spinning something really fast. What happens to the object? The middle of it kind of feels more of an outward tug than the edges of it. So we're going to think about how strong is how much centripetal acceleration is there near the equator if you're living near the equator towards the center of the Earth, because the Earth is rotating. And I'm going to give you a couple numbers, and we're going to kind of switch over to the whiteboard view here. So here's a couple things we're going to need to know about the Earth. How long does it take the Earth to rotate once? I think you guys know that one. What's another important number to know about the Earth? We're going to use heavily in the next couple weeks the mass of the Earth and maybe other astronomical bodies like the other planets or maybe the moon. And we're also going to use heavily the radius of those objects. And by the way, that information is summarized. Where is that information summarized? Well, it's definitely in chapter 13 on page 367 of the textbook, but it's either in the front or back cover. Some of the key numbers are on the front cover. I was looking for a really thorough list, which is one page inside the back cover. They have a little table called Planetary Body, and it lists sun, moon, and the 8 planets. And it gives 4 pieces of information. What is the mass of the object, like the Earth or Venus? What is the average radius of Earth or Venus? What is the rotational period, time to rotate once? And what is its average distance from the sun? Or in the case of the moon, it lists the average distance from Earth. So here's a couple numbers. Mass and radius of the Earth are the first 2 things on the front cover, and there's more information on the back cover. The mass of the Earth is 5.98 times 10 to the 24 kilograms, and the radius of the Earth is 6.37 times 10 to the 6th. We're not going to need the mass number for right now, but we will eventually today. Mass of Earth equals 5.98 times 10 to the 24 kilograms. Very big. Radius of Earth, which is a bit of an average because, of course, it's not a perfect sphere, but it's not bad. 6.37 times 10 to the 6th meters. We're going to use those 2 numbers a lot. And right now I'm going to focus on the radius. What's the rotational period of the Earth? 1 day. Okay. Now I'm going to switch over to the other camera. Click, click, click. Okay. Zoom in there a little bit. Okay. So let's see, how far this way can I go? Right about there. I'm going to go right here. I'm going to say RE is 6.37 times 10 to the 6th meters. And I'm going to say capital TE, capital T for period. What is the period of rotation of the Earth? So this is for the rotational motion, not for the orbital motion around the sun, which would be another very important process. Capital TE, and that of course is 1 day. And then I'm just going to draw like a top-down view of the Earth. Imagine you're looking down on the Earth, you're looking right at the North Pole. So the North Pole is right in the middle, and you're seeing the equator at the edges. That was a pretty good circle, I'm going to be honest. It's about as good of a circle as I can do, I think. So this is the equator. And this is maybe going to be the North Pole. So this is a top-down view. What about a side view? I'll do a side view over here in a different color, just for comparison. Gosh, that was not a good circle. That was terrible. Okay, so this could kind of be, this is trying to be kind of a three-dimensional view, where the North Pole is right up here, the center of the Earth is right there, the South Pole is at the bottom, of course. Whoop. Cap is running away from me pretty effectively. And then I'm going to draw the axis of the Earth like this. Okay, and then the equator, is this red band here. Let me take a look at that. It's not too bad. Okay, so first things first. Ready? First question. Which way should I draw the rotation as moving? If I look down at the North Pole, which way is this thing spinning? Is it spinning like this, or is it spinning like this? Now, that's not a hugely important fact for doing the calculations, but I think we should get this right. Which way is every point on the Earth spinning? Is every point on the Earth, I'm going to use the 3D view, is every point on the Earth moving towards the east as the Earth rotates, or is every point on the Earth moving towards the west as the Earth rotates? So what do we perceive the night sky to be doing? What do we perceive the objects in the sky to be doing, like the sun over the course of the day, or the moon? Things rise in the east and kind of move across the sky throughout the day. They're high in the sky in the middle of the day. They're moving west and they set in the west. So if I look at the sun from the rotating Earth and I see the sun and all the stars as well, all the stars and planets kind of make progress across the night sky or daytime sky from east to west. What does that actually mean the Earth is doing? It's not actually that the sun's zipping around the Earth in 24 hours. It's that the sun hardly moves in 24 hours. The distant stars hardly move in 24 hours, and the Earth is rotating the other way. So the Earth is rotating towards the east. And most of the stuff in the solar system is moving either around the sun in that same kind of easterly direction, or it's rotating in place in kind of the easterly direction. So I'm going to kind of show a little arrow on here. The rotation is kind of this way. It's kind of heading east away from west. So what happens as we rotate towards the east? Things that are out of view below the horizon come into view above the horizon, and then we rotate, and pretty soon they're straight overhead or nearly straight overhead, and then a couple hours later we've rotated past them and they're kind of setting in the west, or they're low on the horizon to the west. So in this view, how should I show that? In this view, if you look down on this from the North Pole, I would see, I'm trying to say this from one to here, counterclockwise, right? Does that sound right to people? That in this view, towards the east is kind of counterclockwise if you're looking down on the North Pole. Okay, so is that right? I know that's right. I'm just saying it to myself one more time. Yes, that's right. Okay. Okay. And what is the radius? The radius is RE. When an object is moving in a circle, what do you know has to be true from the point of view of Newton's laws, or sorry, from the point of view of acceleration and the rules of kinematics? If you're moving in a circle, even if you're moving in a circle at a constant speed, you have to be accelerating, right? And you have to be accelerating towards the center of the circle. What's going on? Okay. You have to be accelerating towards the center of the circle. So what do we call that kind of acceleration? Centripetal acceleration. So the reason different points on Earth, the number one driving reason that some of the numbers in that chart were different in Kuala Lumpur than in Anchorage, Alaska, is because of altitude. How far you, sorry, not altitude, latitude, misspoke, latitude. So let's see, here's the question. We're going to try to calculate what's the centripetal acceleration of the equator due to the Earth's motion, due to the Earth's rotation. And I think we'll answer some other questions along the way, like what is the velocity at which the equator is moving? Okay. And then we'll do it again for other spots like the North Pole. Maybe we'll do it for Minneapolis. What's the formula for centripetal acceleration? Centripetal acceleration is velocity squared divided by radius. And we're going to do this pretty often. Here's the summary. Radius, period, velocity, and centripetal acceleration. Centripetal accel. So I'll say that's R, T, V, A, C. If you know two of these four, you can quickly calculate the other two. We know two of them for the Earth. So we should be able to come up with the velocity. We know two of these for the equator. So we should be able to come up with the velocity of the equator and the centripetal acceleration of the equator. So how do you find the velocity? And you could say speed. Maybe I should say speed. Velocity or speed would be all right here. I'm not talking about the direction of the vector. I'm talking about the magnitude of the vector, and we call the magnitude of velocity speed. So how do you get speed? Speed is distance over time. So how far does the equator move in what period of time? It goes one circumference in one period. So let's just do that and calculate the velocity of the equator. I would like to get the answer in meters per second. So maybe we'll convert it to miles per hour as well, but I don't really want the answer in meters per day. I'd rather have like meters per second. So let's first of all convert 1 day into seconds. How many seconds is in a day? 1 day times 24 hours in 1 day times 60 minutes in 1 hour times 60 seconds in 1 minute. So 24 times 60 times 60. And what is that? 86,400 seconds. So I'll just put that up here. 86,400 seconds. So what is the velocity? Here's the first equation. 2 pi r over t. Distance traveled is circumference. Maybe I'll just say circumference and then, pop that in there. Circumference over period. Distance for one revolution, distance for one rotation divided by time for one rotation. Capital T means period, the time for one full cycle of a repetitive motion. So 2 pi r over t, easy enough, circumference, and 2 pi times, oh, that's the wrong number, 6.37 times 10 to the 6th meters over 86,400 seconds. How fast is the equator moving? And I get I got 463. Anybody else? 463 meters per second. Okay, so far so good. And then how do I get centripetal acceleration? Centripetal acceleration is v squared over r. I want to know how fast you're moving around the circle, and I want to know the size or radius of the circle. And this is our typical picture. We've drawn this one before. Velocity would be like that, and it would be at 90 degrees to the radius. And then what direction is the acceleration point? The acceleration, I'm going to move this. The acceleration points inward. We've drawn this before. It's been probably a month or more since we've drawn this, but we did do a fair amount of this. So I'm just going to call this the r vector in red, the velocity vector in blue, and the centripetal acceleration vector in black. Centripetal acceleration always points at the center of the circle. Velocity, if you're moving around a circle, is tangential to the path, and acceleration is inward. So what do we get for centripetal acceleration? I don't know if this is fully going to be on the screen. AC is velocity squared over radius. We got the radius here is capital R, 463 meters per second squared, divided by the very large radius of the Earth, 6.37 times 10 to the 6th meters. And I get 0.034. I'll do 3 digits. 0.0337. Okay. So what does this have to do? What do the numbers on the board have to do with the gravity values near the equator? If there was no rotation if there was no rotational motion for the Earth, you would get a value for gravity of about 9.83 meters per second squared. But near the equator, we don't get 9.83, we get something less than 9.83, more like 9.80 or so. And it's because the equator is accelerating at this 0.03. So what if we redid these calculations at the North Pole? How fast is the equator moving as the Earth rotates? 463 meters per second. By the way, how many miles per hour is 463 meters per second? I'm going to do the conversion. I'm looking at the conversion on the inside cover of the book. And you multiply by 2.24. That's a little over 1,000 miles an hour. That's how fast the equator is moving as the Earth rotates. How fast is the North Pole moving as the Earth rotates? How fast are points on the axis of the Earth moving? They're not moving, right? The North Pole is kind of rotating in place, but it's not executing a large circular path. So if the North Pole isn't moving, what's the centripetal acceleration at the North Pole? Well, there isn't any, which means there's a 0.03, about a 0.03 meters per second squared difference in acceleration in measurements of G at the equator, or points near the equator, compared to the poles. What about Minneapolis, Minnesota? How do you adjust this for a latitude other than the equator or the North Pole or the South Pole? What you're going to do is you're going to replace R. What's the radius of the equator circular path? That's RE. What's the radius of Minneapolis's circular path? And you can draw a little triangle out. It is, if you're at a latitude other than equator of 0, you replace radius of the Earth with radius of the Earth times the, just a second. I lost it for a second. Times the cosine of the latitude. So if you're at equator, you're at latitude 0, cosine of 0 is 1. If you're at the North Pole, which is positive 90-degree latitude, cosine of 90 is 0. And then you'd get some zeros in there. What about Minneapolis? What's the latitude for, let's say, somewhere close to where I am? I don't know where you guys all are. I'm in Roseville, Minnesota. What's the latitude in Minneapolis? You might remember this from the an intro day, when like the day you arrived on campus, maybe in the fall, and we had an engineering meeting, kind of get to know people meeting. It was in the Nazareth Chapel down the hall from where I am, and you might remember there was some quiz questions, and one of them was, right now when you're standing on campus, are you closer to the North Pole or are you closer to the equator? And it turns out you're dang close to halfway in between the North Pole and the equator when you're on campus, because Minneapolis and the suburbs of Minneapolis and St. Paul are very, very close to 45 degrees north latitude. Officially, where I am on campus, I am a couple miles north of the 45th parallel. So basically, I'm going to use 45 for that. So if you adjusted this for Minneapolis, you would get some number smaller than 0.03, but bigger than 0 for the poles. And then here is how you calculate the acceleration of gravity when you know how far away you are from a planet. Here is the key equation. This is the equation for Newton's theory of gravity. How do you calculate the force between two objects? What have we been doing all semester long when we have to calculate the force, the force of gravity between two objects? Well, pretty easy. We have just done m times g, and we use a little g value. And it doesn't matter where exactly on Earth you are, we'll say, oh, g's about the same. And it won't really matter if you're up in the sky on 2nd floor, 4th floor, 20th floor, or ground level. We're going to use basically the same g value. When you do Newtonian gravity, you can't pretend like gravity is the same strength at all distances outward from the Earth. It gets weaker with distance. And Newtonian gravity describes how it gets weaker with distance. So kind of hold on to this 0.03 number, especially that 0.03 meters per second squared. And then let's calculate Newton's theory of gravity. Maybe I'll leave that there for now. Probably it'll eventually get erased. I'm going to do it like this. Near Earth, we do what for gravity? We say the force of gravity is mg, down. Right? Maybe you could say something like negative mg j hat. What about Newtonian gravity? Which is basically chapter 13. What do you use in place of this? You don't use this. You do this. The force of gravity depends on how big one object is, how big the other object is, and how far apart the two objects are. So the picture here is, I got a little box with mass m. And then I got the ground. The picture here, we zoom way out and we say, no, I've got one object, that's too big. I have one object here, and I have another object here. And this one is mass little m, but this one is another mass. You could either call these m1 and m2, or a lot of times we'll call one of them lowercase m, one of them capital M. But anyways, you have two objects. And what do I need to know to calculate the force of gravity according to Mr. Newton? I need to know how many kilograms that object is. I need to know how many kilograms that object is. If you replace the Earth with a bigger mass, gravity gets bigger. if you replace this block with a more massive block, gravity gets bigger. Excuse me. And the distance between them is the other really key piece of information. How far is it between the blocks? And we'll usually call that R for radius. Kind of R is generally a variable often used to keep track of the separation between two objects. The R to use is the center to center distance. R is the center to center separation. If the objects are pretty small, you could just say it's the distance between them. But let's say one of the objects is like the Earth and it's pretty big. If I'm going to do this, and I got to put one more thing in here, there's a constant you look up called capital G. So I need to know two masses, one distance, and look up this number called capital G. Over here, I look up little g, and I know you guys know little g. What's the value of little g? What are the units of little g, etc.? Over here, don't use little g in the next 2 weeks very much, okay? We use it heavily almost every other unit or chapter of the course. We're not going to be using little g very much because little g only is true if you are near Earth. And there's a different value of little g near the moon, but it only applies if you're close to the surface of the moon. Maybe you're within, you're near the surface of the Earth, or maybe you're a mile below the surface, or maybe you're a couple miles up into the atmosphere above the surface, but that still counts as near the Earth. But what if you're the moon? What if we want to calculate the gravity between the Earth and the moon? We can't do mass of moon times 9.8 because gravity is not nearly a value of 9.8 out to that great distance. We have to use this. And the important thing to know here is, how do you determine R? And what's the value of capital G? Capital G is in the front cover of the book. It's the fourth constant in the front cover of the book. What's the value of capital G? It's usually called Newton's constant or just big G. Newton's constant, a lot of times we just call it big G. And what's the value? 6.67 times 10 to the negative 11. I'm typing it into the chat here. Newton meters squared over kilograms squared. And we'll use this number all the time. It's the fourth constant in the inside front cover of your textbook. Newton times meters squared over kilograms squared. This number is much, 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 much more important in the study of physics than this number over here. Because this number over here only matters if you're near Earth. This number over here matters whenever gravity is involved. Now, how are these two linked? How are these two linked? If you're near Earth, these two should give the same answer. So the link is, if you're near Earth, these should agree. And if you set these equal, they both have a factor of little m. So both the near Earth version and the real Newtonian version, both versions say the more mass for the block, the greater the force of gravity on a block. Both of them are proportional to little m. So if you set them equal and then you cancel off little m, the link is little g is capital G times capital M, and I'm going to call that, I'm going to put a radius down here, and then we're going to calculate it. We're going to do this for the Earth. What's capital G? Bam. what's the mass I should use? I should use the mass of the Earth, because the mass of the block is the one that canceled out. The mass of the Earth is the one that didn't cancel out. And what should I use for little r? Let's say I'm standing right here. Let's say you guys are sitting in a chair somewhere in your house. How far are you from the Earth in this way of thinking about it? The answer is not, well, I'm on second floor, I'm looking out the window here, I'm on second floor, so my radius value is like 20 feet. No, 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 no. How far is it from the center of me, somewhere kind of in the middle of me, and I'm so small, it doesn't hardly matter. Let's just say, how far is it from the center of me to the center of the Earth? That's basically the radius of the Earth, right? Because from the center of the Earth to the edge of the Earth is capital RE, which is thousands of miles. And then maybe I'm on second floor and you add 20 feet, but 20 feet's pretty unimportant if you already have thousands of miles. So a lot of times we'll call this capital R if it's the radius of a planet. So if you want to know the value of G on Earth, you do capital G times the mass of the Earth divided by the radius of the Earth squared. And I'm just going to do that now. I highly encourage you to practice typing this stuff into your calculator. There's lots of scientific notation, powers of 10, large positive or large negative powers of 10. The mass of the Earth and the radius of the Earth are listed in the chat up above. So from this perspective, let's see what we get if we just calculate capital G mass of Earth over radius of Earth squared. And let's do this, and I'm looking for one thing. And it'll bring up a calculator here in a second. Come on, where's my calculator? Okay, so I've got 6.67 times, actually I'm going to do it like this, 6.67, and then I would do E, oh, what happened? 6.67 E, nope. Oh, man, that's awful. Sorry. E negative 11 times mass of Earth is 5.98. E 24 divided by parentheses radius of Earth 6.37 E6, that's the radius of the Earth, and that gets raised to the second power. What did I do? That's the wrong minus sign. That's what I did. Okay, and I think it's good. Okay, what number do I get right here for gravitational acceleration? It looks pretty familiar to us, but if I do this for Earth, what do you see that I got? 9.83. I'll go 9.830 basically, I think. So I'll just leave it here. I won't do another digit. How do you guys feel about 9.83 meters per second squared? It's a little different than we've used all semester long, right? Why have we generally used 9.8 or 9.81? A lot of books do that. It's not just because we want to round it off and make it easier. It's because this would be the value if the Earth weren't rotating. This would be the value everywhere. And this is very close to the value at the poles, but you should take this and you should subtract off the centripetal acceleration because that's kind of how that works out, is 0.03 of this is eaten up just to keep the object moving with the Earth's rotation. And that only leaves aside the remaining about 9.80, especially if you're near the equator, to be actual acceleration of the object towards the surface instead of just helping the object rotate with the surface of the Earth. And if you go close to the poles, you'll get closer to this number because the poles don't experience any centripetal acceleration. For our purposes, unless the problem says otherwise, basically think of the Earth as not rotating for the questions. Now that's not a big effect, but like we saw, that's like a 0.03 kind of effect. You might almost get in the habit of thinking that little g is 9.83 if you want to do comparisons of near Earth version of gravity to Newtonian gravity. So let's see, we got 12 minutes here, maybe less. Let's talk about a couple things. Number one, the units. The units work out Newton times meter squared over kilogram squared. You multiply by kilograms times kilograms, that cancels kilograms. You divide by radius squared, that cancels mass squared, or meter squared, and you get newtons. So this gives you a force in newtons, as it ought to, because it says Fg. Oh, what's the direction of this force? This points down, and this, of course, is attractive. Gravity is attractive. So it's like this object is feeling a force that way, Fg, and this guy is feeling a force that way with Fg. Remember, forces are equal and opposite, so when you calculate this, this is the force that little m is feeling that way, and it's also the force that capital M is feeling that way, directly at one another, attractive. I'll just say attractive for a direction. And you see the comparison works out better if you think of this as 9.83. Let's see. What about the value of capital G? How big is this? 6.67 times 10 to the minus 11. So big G is not very big. Big G, capital G, is 0.12345678910 667 Newton meters squared over kilograms squared. You know, it's very, very, very small, right? And the R's are usually pretty big R's. So G is really small, very small. R is usually quite large. How do you ever get a force that's not incredibly tiny from this calculation? You got to have one of the masses be humongous, right? Do they both have to be humongous masses? No, it could be mass of Earth and mass of person, and one of the two needs to be enormous. Because if both the masses are around 5, 10, 15, 100 kilograms, then you're going to have 100 kilograms times 100 kilograms is 10 to the fourth. You're going to multiply by 10 to the minus 11, divide by something huge, and you're going to get an incredibly tiny force of gravity. So here's the next most important thing to say about Newtonian gravity, which I should have said first. Which objects are affecting one another via gravity, according to Mr. Isaac Newton? Which objects are pulling and pushing on which other, or pulling, I guess, I'll just say pulling. Which objects are pulling on other objects via gravity, according to Mr. Newton? Everything. According to Mr. Newton, there's gravity between me and the desk. There's gravity between me and all the chairs in this room. There's gravity between you and the wall. There's gravity between you and anyone else who's in your house. Because it's mass of 1 times mass of 2 over distance squared. Is that how you and I typically think of gravity? No, we typically think of it as just kind of in this view over here, we typically think of it as just between Earth and other objects. But in Newtonian gravity, it's between everything. Now, how can that be? How could he possibly say that I'm being attracted via gravity to that chair over there? Well, let's estimate the calculation. What do you think the mass of a person is? What do you think the mass of a chair is? And how far apart do you think? I'll give you an estimate for the distance of me to the chair. The mass of me, let's just say, 70 kilograms. Mass of the chair, let's round up and call it 15 kilograms. And I'll tell you that right now, my distance to the chair is, I'm going to say 2 meters. I'm keeping a good 6-foot separation to that chair. What do you get if you plug in 70 kilograms, 15 kilograms, 2 meters, and capital G? You're going to get something insanely small, right? so small that it's hardly worth talking about. Let's see what the number is. 6.67. Hello. 6.67 times 10 to the negative 11 times, let's say 70 kilograms for a person. I'm going to round way up and say 15 kilograms for a chair. And then I'm going to divide by a distance of 2 meters squared. And I get, that silly negative sign thing again. Okay. Let me do one thing. Why would that be an error? I think I did it correctly that time. I thought I did it correctly that time, but I think right here, it doesn't like my minus sign. Oh, gosh, so slow. Sorry, everybody. This is all messed up. Anyways, you get something very, very small. I'm going to let that go because that was frustrating. You get something incredibly tiny, right? So Newtonian gravity is also called universal gravitation. Why is it called universal? All objects participate in it. All objects attract all other objects via gravity. But usually the force is incredibly tiny unless one of the two objects is enormously big mass. And if they're both enormously big mass, fine, but you got to have at least one of them be huge. Okay, so here, let's wrap up by doing this. What's the value of little g near Earth? 9.83 meters per second squared. Take a guess. Let's say you're not on Earth, you're not standing on the Earth or very close. Let's say you're in orbit around the Earth. Let's say you're on the International Space Station, because I can look up information about the International Space Station pretty easily. What do you think the acceleration of gravity due to Earth is for astronauts on the International Space Station? It weakens from 9.8. As the radius from Earth gets bigger in the denominator of the equation, the force comes down, and if the force comes down, the perceived g value comes down. What do you think the value is up near the space station? Is it's less than 9.8. Do you think it's like, do you think it's around 9? Do you think it's around 8? Do you think it's around 3 meters per second squared? Do you think it's less than 1 meter per second squared? Just what would you guys guess? Somebody says maybe about 1/5 the value we experience. We're around 10. Maybe it's around 2 meters per second squared. Okay, how about reaction to Titus's guess? Who votes higher than 2 meters per second squared for acceleration of gravity at the space station? And who votes less than 2 meters per second squared at the space station? You can place your bets. I'm going to bring up some information about the space station. Where's the web? Oh, that's a good one, but that's not what I'm looking for. Oh, Sanders drops out of presidential race. New information to me. Okay, I'm typing in International Space Station. And I'm just going to go Wikipedia. Actually, I think the information I need is already in the sidebar here, but I'll just click on this so we can see some other information about the space station. Okay. I think, no, it's over here on the right, and I'm not able to see that. Okay, let's make this bigger for you guys. Okay. See this information over here on the right of the screen? I'm looking for the altitude, or the distance above the surface of the Earth. Altitude, and I'm going to look and see if there's some more information, but I think that's pretty good. Okay. So here's what it says about altitude. Ready? 408 kilometers at the lowest altitude, 410 kilometers at the highest altitude. So I'll just use 409 kilometers as an average altitude. And I'm going to do this calculation up here on the board for the space station. Here's the mass of the space station. I might write that down, but that's going to cancel out if I'm calculating acceleration. It would be relevant to calculating force in newtons, but not acceleration in meters per second squared. 409 or 408 or 410. Okay, let's do this and wrap up. Okay. And here we go. Force of gravity is kind of like m little g, capital G, capital mass of Earth, little m, and little m means the space station. But, you know, it's going to cancel out. And now what should I put in here for the radius? The radius is not 409 kilometers. 409 kilometers is the distance above the edge of the Earth to the space station. So what is the distance from the center of the Earth? I have to add on the radius of the Earth. So I'm going to type in 6.37 times 10 to the 6th meters plus this. I would often call this the altitude h, and you want to add the radius of the Earth on to get little r. I don't want to know how far the satellite is above the edge of the Earth or the station. I want to know how far the station is from the center of the Earth. So it's radius of the Earth plus an extra 409 kilometers, and I'm going to put that into meters, and I'm going to add on an extra 409,000 kilometers. I know it's probably hard to see, but there you go. And then we can just type these guys in. Mass of the Earth is 5.98. Gravity is 6.67. And this is what we get. 6.67 e to the minus 11, 5.98 e to the 24th, divided by 409,000 meters squared. Anybody do that and see a number that you get? I did it, and here's the calculation I came up with. Little g at the International Space Station equals, I got 8.68 meters per second squared. Anybody else? Just pop it into your calculator. Should get about something in the high eights. Anybody agree? So what do you think about that? Was it bigger or smaller than 2? It turns out, well, it's definitely less than 9.8 meters per second squared, but it's not a ton less. It's like 1 meter per second squared less. Why? Any thoughts as to how that number could be so large, and yet it seems like the astronauts in the International Space Station, you know, if you see videos from there, for example, they seem to be kind of in a fairly weightless environment? Think about that. Farther distance between masses. So that's what brought the number down from 9.8 to 8.68. But that's still a pretty, I don't know, it's like still a pretty decently big acceleration. So anyways, that's just a thought that is the value at the International Space Station. They're constantly in free fall with the curvature of the Earth. They're orbiting around the Earth. I think those are the insights that are most relevant to what you would see or experience if you were an astronaut in that space station. The astronauts are falling around the Earth or orbiting around the Earth with the space station. And all you really see or experience while you're inside of a certain environment is, am I accelerating differently than the walls? You know, if I jump here in place, the room isn't accelerating, but I am. And so I kind of feel the ground come up towards me. So they experience essentially a sensation of weightlessness because they are in free fall with the station. And in this case, free fall isn't like falling towards the Earth, it's orbiting around the Earth. But free fall just means motion only affected by gravity. And the station's motion is only affected by gravity, and the astronauts' motions within the space station are also only affected by gravity. So they're in mutual free fall. And it's a pretty big number of 8.7. If you drew this to scale, how much is 409 kilometers compared to the radius of the Earth? The radius of the Earth is over 6,000 kilometers. If you go up in the space station, you're adding on an extra 400 kilometers, which is big compared to you and me, but it's not that much further away from the center of the Earth than we are right now on the surface, because 409 isn't that big compared to over 6,000 kilometers for the radius. And of course, you could continue this out. What else could we calculate? How strong is the acceleration of gravity at the moon? How strong is the acceleration of Earth's gravity at the moon? We could do that. Just a couple follow-up questions. What I said previously, radius, period, velocity, and acceleration, right? And what did I say? If you know two of those four, you can find the other two. Well, we got the radius, and the acceleration is the 8.68 number. G is basically the same as acceleration. So I've got acceleration and radius. So I think a good follow-up thing to do is calculate what is the velocity of the International Space Station as it orbits the Earth. Very easy. I use centripetal acceleration, and I take the acceleration and I set it equal to v squared over r, calculate velocity, and then find the period. How long does it take the International Space Station to orbit the Earth one time? And I'm not going to do the calculations. I'm just going to show you the answers because I think they're on this page. What is the orbital speed of the International? Here's the altitude information again. What's the orbital speed? Around 7.6 kilometers per second, or however many miles an hour that is, it says. And what is the orbital period, the time to complete one orbit? 92.68 minutes. The International Space Station, due to the acceleration of the Earth, orbits the Earth once every about hour and a half. It's very easy if you have an acceleration to calculate this number, and it's very easy once you have the speed to find the time, because we know the radius. We know the radius not of the Earth, the radius of the orbit is what matters here. Okay, I think we'll leave it there. We're going to do a lot of calculations with this. Most of the homework, there's only 5 questions due this week, which is going to be due Monday. They're mainly about circular motion, not about gravity, but they're going to use the acceleration equals v squared over r, and they're going to use velocity equals 2 pi r over period probably a couple times. That's it for today. You guys are dismissed. I'll see you tomorrow for lab, and the lab can be submitted on, last week's lab can be submitted on Moodle anytime. Okay, have a good Wednesday. See you in lab tomorrow. Bye, Rockford. Bye, Ashley.